problem with Chem? What is the change in internal energy when the system loses 513 kilojoules? And so 513 kilojoules is it positive or negative? If the system loses, it'd be negative. So we have to assign the sign here. So loses is negative, so minus 513 kilojoules. And does 812 joules of work. 812 joules is positive or negative? That's also negative. So the internal energy is the heat plus the work.
Then you have to convert them both to either kilojoules or joules. In this case, kilojoules.
Yeah. Oh, if I, when you're going through like tests quickly, you have to watch out for certain things. Like, I would have done this. I would have just said, okay, minus 513 plus a minus 812. Minus 513 plus a minus 812 is minus 1325, right? And then I would have picked it, B. But it turns out that would be, it's a trick question, sort of. This is like, did I tell you I took the algebra test, GRE math? Algebra test. And I was algebra, I didn't study at all for it. And then when I saw my score, I was shocked. I was shocked because I thought it'd be easy, easy, high score. Then I went back and I looked at it, and there are little things like this, I would just add those. I wouldn't really look at the units because I was trying to do things quickly. So I made a bad error. But here you can't add, this is kilojoules, this is joules, so this is going to be 0.8. So that should be minus 513.8, which is going to be minus 514, which is 8. Okay. Uh-huh.
For number 12, can you please explain why EO3 is a state function?
I don't know. What did you guys put? State function or no? Not a state function.
True.
You put true because why? Why is it true? There's a restriction, yeah. It depends, it depends on how tricky I want to get. But, in these questions, you could, QP, in order to be a state function like delta H, is that all we have to restrict QP to? In order for QP to be a state function like delta H, we have to restrict it to constant pressure, which it is, constant pressure.
And no work.
Not no work, only one type of work. What type of work is it?
Constant volume work.
Mm-mm. QP, you can't have under constant volume conditions. It should be wrong. Found my charger. Cable. I think this is mine. You don't have the definition of delta H memorized by now? What is the definition of delta H? Change of enthalpy. Well, what is enthalpy then? A lot of people will tell me mathematically what it is.
Yeah, delta U.
Is that the definition of delta H? Is that how it's defined?
Well, isn't it? Delta H equals delta U equals Q. No, well, but when work is, because it can just be Q if there is no work.
Not if there's no work.
It's not if there's no work.
Yeah, there can be work.
So then could it be delta H equals delta Q when,
This is the definition of delta H. But there's one more thing that has to be restricted. What is it?
when it's not cost and volume?
It has to do with work. There's one more thing that's missing here in the definition. This is not the complete definition. There's one more restriction that's missing.
When work is done on the system?
Not work is done or work is done by. But it is constant pressure. That's what this is. So it's restricted right now to constant pressure.
What's
There's one more restriction on this.
Does it have to do with the mole to mole ratio of the reaction?
It doesn't have to do with it mole to mole. It doesn't have to do with what kind of reaction it is, or it doesn't even have to be a reaction. It could just be a phase change or
Oh, it
some
has to be a gas.
process.
It has to be a gas from.
Well,
Gas to
no,
gas.
it doesn't have to be gas to gas. It could be liquids too. Constant temperature is given usually. We do this at constant temperature, but that doesn't even have to be constant temperature, because if it's not a constant temperature, then you have to do a object and a reaction process. So what you do is a reaction or process to get it to the same temperature, and then you heat the remaining object or cool the remaining object to get to the final.
It doesn't depend on that.
Right. It doesn't depend on the path. Right now, heat depends on the path. To make it independent of path, you restrict it to constant pressure or constant volume. I can do that too. If I restrict it to constant volume, then that's easy, you know, because we know that delta U is equal to QV. Technically, it's this. QV is equal to the amount times delta U. And because QV is not on a per mole basis, delta U's are usually on a per mole per basis. So just, you know, how many moles would you have? So it's amount times delta U. But, you know, it's the same thing. Q and UV, delta U are the same. It's just Q's the amount of heat you get for the specific amount of reaction you do. Delta U is the amount of heat you get per mole of the reaction you do. No, they're the same thing, essentially. Well, think about it and look and then see, is there another restriction or is that it? Just constant pressure? Is that it? Or is there a restriction?
You're not finding anything else, are you? Yeah, that's why I asked. Because it doesn't have to be
That's the initial balance. It was at the endothermic reaction.
when there's no volume change. Look, watch. Delta U equals QP plus W.
No volume and no pressure change. I know like the pressure change is like inherent.
Yeah, so when there's no change in volume, work
Like
becomes
solid
zero.
volume.
So delta U equals QP equals delta H. When volume doesn't change, volume's unchanged.
If it expands. Look at the gas.
I think it's that.
And if it stays the same state.
When volume is
it expands,
unchanged.
right? So it's the same. I think that's why it's called the state function.
So it's not that volume is zero or that there's no work done. Volume's unchanged.
Wait, so it's set.
It does have to be work. When volume's unchanged, work is zero.
That's the definition. Because work is zero, I mean.
Yeah, work is zero when it's constant volume, right?
Could it be when volume is unchanged?
No.
Really?
It's not when the volume's unchanged. Does someone figure it out? Yes, that's it.
What? Restrict work?
No, work is not zero.
But you restrict work.
Yes, you do restrict work, but work is not zero.
To negative P delta V.
But isn't that just saying constant volume? I mean, no, constant pressure. You use negative P delta V when there's constant pressure.
Well, negative P delta V work is always going to happen at constant pressure, right?
Yeah.
Because that's the natural work of a chemical reaction.
Yeah.
And so you have to restrict the work. But, like for example, if you burn a mole of methane,
Mm-hmm.
at constant pressure, you're going to have negative P delta V work, and you're going to get a certain amount of heat. And so let's say you burn the mole of methane on the laboratory burner versus burning a mole of methane in one of those, you know, those CNG vehicles, compressed natural gas vehicles.
Mm-hmm.
Both of those happen because you don't put the car. Do you put the vehicle inside a bomb? No, both of those happen out in the open, right? Are you going to get the same amount of heat if you burn a mole of methane, 25 liters, here versus burning it inside a car engine? Would you get the same amount of heat?
Yeah, you should.
Well, it's constant pressure.
You should.
Or, let's say, rather than using a CNG, have you ever seen those methane fuel cell cars? You know what methane fuel cell? You know what fuel cells do? Let's show you. Well, we can shop her, maybe. I don't see any methane fuel cells there, though. It's coming up. All right, this is a methane fuel cell kind of schematic here. Even though it looks a little bit complicated, essentially you're taking the methane and converting it into CO2 and water. And so you have methane and oxygen going to CO2 and water.
Mm-hmm.
This fuel cell, do you put it into a bomb, a stainless steel bomb, and then lock it tight? No, this is done at constant pressure. So if you put methane into a fuel cell, what does a fuel cell do? A fuel cell generates electricity. That's like those hydrogen fuel cell cars. And so here, what we want to do is we want to maximize the internal energy. That is, in this case, well, we want to maximize the delta H and convert it into work. What kind of work? The work of generating electricity. So does this generate any electricity here? This doesn't generate any electricity. So if I burn a mole of methane here, I'm just going to get all heat, right? But there's natural work of the chemical reaction taking place. That work we can't help because it's being done at constant pressure, right? The same thing here. We can't help it. The natural work of the chemical reaction is taking place here. But instead of releasing all that excess energy as heat, we want to not release it as heat. We want to convert that excess energy into electricity. And so do you think this is going to get just as hot as the flame? No. So both of these are constant pressure. But both of them are going to give you different amounts of heat because both of them will do the natural work of a chemical reaction, but this one we're trying to get extra work out of this. And the extra work is going to be generating electrical work, you know? Or if we look at a CNG car, how does a natural gas engine work? Essentially, a CNG car functions the same way as a gasoline engine, except you're not burning gasoline, you're burning natural gas, which is methane. So do you think in a CNG car you're going to get the same amount of heat? No. Is it this flame burning? No. You're trying to get more mechanical work out of this. So let's see some images here. See, so they have tanks. And so they don't have a bunch of Bunsen burners underneath the hood generating heat. You know, and maybe that heat is converting water into steam, and then you got a little steam engine in there going, right? You know, I was reading something about these small towns, this small town in Kansas. And they're talking about, you know, they had a whole bunch of small towns at regular intervals. They had a whole bunch of small towns at regular intervals because the old steam engines would have to be refilled with water. You know, they run out of water, so each small town had a big tank where it could refill the steam engine with water. But that's not how we generate propulsion here. You know, you generate it rather than converting into heat and then using that heat to warm up we want to bypass the heat altogether and go straight to work. You know, that's converting chemical potential energy into mechanical work. Does that make sense? And so the situation is here, if we don't restrict the work, then well, it depends. We could do lots of reactions under constant pressure. You know, we want to do lots of reactions and figure out different ways we could use the chemical potential energy stored in the natural gas.
Yeah. So how do you constrict the work then?
How do you restrict work?
Yeah.
Sabrina had a good answer. Well, you said you restricted to minus P delta V work only. And so this is the definition, assuming that
You use
work, the only work that's done by the system or on the system is P delta V work. That's it. And you can't have other work. And so the way we see that is this. The way we see that is delta U is equal to Q plus W. Okay, let's restrict the pressure to constant pressure. If we do constant P, then delta U is equal to QP plus W. Then we restrict the work. If this work is only P minus P delta V work, then QP is called delta H. But it doesn't have to be. We could try to get less heat and more work. So we might try to do electrical work. We might try to do mechanical work. The more work we try to get out of this, the less heat we're going to have because there's a fixed amount of energy coming from this. And so we would try to generate more work here. And so that's the restriction because, you know, it depends on how many work terms you're going to add to this. That's going to decrease the amount of heat you get from it. Ideally, it would be perfect if we could convert it all into work, you know. But it's very hard to convert it efficiently into all work. You know, you're going to have frictional losses. You're going to have all kinds of other stuff that's going to result in heat. Does that make sense? So I don't remember how tricky I was going to try to be this particular semester. To be honest, I don't remember. But you know, it's not meant to be too tricky because you could argue this either way. You know, somebody could have picked true, and just said, "Oh, I automatically assumed that work was only P delta V work." And then maybe it's okay. You know, that's an acceptable answer if they automatically assumed only P delta V or natural work or chemical reaction. Or somebody could have picked false because since work was not specified, you know, there are lots of different kinds of work. You know, stretching the DNA or whatever that one was. Was that stretching the DNA? That kind of work, you know. Yeah. And other types of work. Electrical. So sometimes I accept both answers depending on what, how people were thinking about it, you know. Because both answers are correct in their own way, you know.
So we write like our reasoning?
No, I think I picked B for this, but some people came up to me and said, "Why wasn't it A?" A, it should have been A, you know, and then. But you could, of course, you could write your reasoning on the test, because you can write whatever you want on the test and then hand it in, and then see, I had it down. That's better if you just write down, you know, your thinking. This is why I like to collect all the scratch paper, because some people will come up to me afterwards. I knew that question. I knew the answer. I had it here. You know. Sometimes people leave the multiple choice blank, and then I thumb through the scratch work and see. They just forgot to fill in the bubble on the scan. All right, so you know, technically, and I said this earlier, there are two restrictions to make heat into a state function. One was constant pressure, and two is restricting the work. And so this is why I would have picked B here, because I said that there are two restrictions, not just constant pressure. That's for constant pressure, though. QP. What about QV? How many restrictions are there on QV? And so, you know, this is the way you have to think about these. You know, the practice test is not just the answer. Some people, they just want the key, you know? But I don't want to give the key. I want you guys to think, you know, if this were QV, is it the same?
No.
If this were QV, what would it be?
Work would be restricted to nRT.
Okay. And so what would this be? Would it be true or false if this were QV?
Be either, because you didn't specify as well.
Well, it also depends on how you do it in a bomb. You know, in a bomb, can it really any work be done in a bomb?
Actually, can take it long.
How? I guess, yeah, maybe. Electricity? If you do it in a bomb?
No.
Okay.
Most likely be just heat transfer from the bomb.
Yeah, maybe you could put your fuel cell inside there. In a bomb, I would lean towards what? I'd say, you know, inside a bomb, I guess it would be kind of hard because I guess you could put, let's say you could put a CNG vehicle inside a gigantic bomb and then run it there, right? Then it would be, so bomb would be less flexible. So if this were QV instead of QP, is it a state function?
It is.
Yeah,
It's true.
it's true. I think on this one, you know, I just marked false, but I accepted both answers because, you know, on the test, not on the test, in lecture I often did this. Remember, delta H is equal to QP. I did that many times, but I didn't say, oh, there's a restriction there. I just said it once or twice or three times, and then.
You said it when we
After.
talked about enthalpy diagrams.
All right, so you want to, when you go through these, after you know, let's say the first time you go through it, you just want the answer. And then the second time you go through it, third time you go through it, fourth time, maybe it starts to get boring, but it doesn't have to get boring because what you can do is you can put little twists into the question, you know, to really test your understanding of this. And so, so you might say, when is Q not a state function then? You know, how would this have been, how would this Q have not been a state function? You know, when are all the scenarios? So you think, okay, what are all the possible scenarios when Q is not a state function? Like QV, it's a state function. QP, yes and no, you know. But we know Q is normally not a state function, so how would it have been written then?
If you asked if Q alone,
Yeah, Q alone. No restrictions on it.
because Q is path dependent. It depends on pressure and volume. for its value.
Yeah.
So if pressure and volumes change, then Q changes, and so does work.
Well, yeah. I mean, pressure volume being pressure volume work, but pressure shouldn't volume should change.
Volume should change.
And then the equation nRT, maybe you should rewrite that as delta n, you know, the change in moles.
Yeah, I meant delta N.
Delta n. Of gas only, you know, not delta n of the reaction. So. All right, other questions? Number 4. All right, calculate the heat liberated when 24.45. That's a special number, 24.45. You have it memorized? What is that? 1 mole of gas at what temperature?
Room.
Room temperature and what pressure?
Constant. Or
Not
constant.
constant, but it is a constant, but what temperature specific? A constant half atmosphere? 1 bar?
1 atmosphere.
1 atmosphere. Yeah. And so we're looking at combusting methane, 1 mole of methane. If we combust 1 mole of methane, how much heat are we going to get?
So that's where Q equals moles times delta H.
Yeah. Right.
So you just convert to moles.
Right. So we convert that to moles. So Q is going to equal amount times delta H. Well, the amount is 1 mole. Delta H is minus 890.3 kilojoules per mole. And so the amount of heat will be minus 890.3, right? Kilojoules.
Mm-hmm.
But we have to be careful because of this. When I say how much heat is liberated, what would you say? Would you say minus 890.3 kilojoules of heat? Or would you say positive 890.3 kilojoules of heat?
Well, if it's liberated, that means it's 1 out, so it should be negative, right?
Okay. All right. So then let me ask you which is correct. You know, let's say if it's liberated, let's say you lost. Because that would be like liberated. I lost a negative $20 bill, or I lost a $20 bill. What would be?
Losing $20.
And so your bank account would be minus $20 if you lost it, or your wallet would be minus $20. But did you lose minus $20, or did you lose $20? 20. And so that's the trick part of this question. Is since I said the heat liberated, then you wouldn't say, well, the heat liberated, I lost $890. You would say, well, $890 was lost. Would you say minus $890 was lost? No, lost by the system. So it actually turns out to be E. None of these, because it should have been positive 890.3 because of the sign. You're correct. When you're doing the math, it would be minus 890.3. But when you're talking about it and you add liberated, how would this be correct? How would A be correct? How would I rephrase the question to make A true? The correct answer. These are the things you think about, you know, because after you've gone through the answers and you go, okay, I know that pretty well, then you want to add twists, you know, adding twists to C, you know. A would be the correct answer if I just changed the wording on this question a little bit. And how would I have changed it?
So like the change in heat.
Yeah. If I said like the change in heat, 124, then A would be correct. It would be no problem, okay? But since I added the word liberated, then that changes everything.
Okay.
Uh-huh.
What's the difference between produce and evolve?
Same thing. Produced, evolved, liberated, lost, they all mean the same thing. That the system's losing energy. Okay, so does that answer number 4 then? Maybe. All right, other questions on this old test?
So then would number 14, based on how we describe QP being, shouldn't it be none of these? Because you're saying no work is done, but technically there is work being done? Well, it wouldn't be A and B anymore.
A reaction carried out under constant pressure involved no work.
Because technically, a reaction carried out under constant pressure, you still have work. You just restrict it.
No, a reaction carried out under constant pressure can have six possible scenarios with work. Do you know what those possible? Because let me give you an example. Can you think of a reaction carried out under constant pressure that involves no work? Just give me an example of a reaction carried out under constant pressure that involves no work. Burning methane involves work under constant pressure. Because burning methane, I don't know, did I write the reaction there? CH4 plus 2O2 with CO2 is 2H2O liquid. This is gas, this is gas, this is gas. Burning methane involves work because I'm going from about 75 moles of gas, 75 liters of gas, roughly 75 liters of gas to 25 liters of gas. And 2 moles of liquid water is like 0.03 liters. 0.03 liters is not that much to worry about. And so 75 to 25 is a volume change. We're losing 50 liters of volume, right? And so there's definitely work involved in combustion methane. That's for methane. For other substances, there might not be much work. For example, xylene. Xylene, you go from 5 moles of gas to 5 moles of gas. So there's barely any change in volume. Negligible change in volume. What about if I had sodium hydroxide and HCl? Let's say I took 40 mils of sodium hydroxide and added 40 mils of HCl. So I started off with 80 mils. How many mils am I going to end up with?
The same.
The same. I'm going to end up with 80 mils. Do the volume change? The total volume initial versus the total volume final is the same. So it's constant volume. Since it's constant volume, did I just do that in a bomb? No, I did that under constant pressure conditions. So that's what we have here. A reaction carried out under constant pressure involved no work. There was no work involved there, except I did work, but the chemical reaction, no work was done on this chemical reaction or by the chemical reaction. And so, how much heat is involved?
So then it can be A and B.
Yeah. A and B.
Yeah, that's it.
Is that it?
That's it.
A and B?
Yes.
Why not C?
Because it's just heat alone, it's not heat restricted to constant pressure.
what if I restricted it to constant pressure?
Then it would include C.
But if I don't restrict it to constant pressure, C is not included?
Yes. I think. Well, technically.
Well, do you guys have these diagrams memorized? I wrote 6 diagrams on the board. And so we start off with exothermic and then endothermic. Energy level diagram. So for the exothermic case, we have something like here, V initial, V final. V initial, V final are the same. This is exothermic, so this is delta U. This is constant pressure. This is P delta V work only. So delta U is equal to Q plus W. Right?
Mm-hmm.
Well, Q in this case can be any Q, but look, it's already restricted.
Oh, okay.
I mean, isn't this one restriction, constant pressure?
Yeah.
And so that's QP. This is equal to QP plus W. Well, don't we know that W is 0 because no work is done? 0. And so it's the same thing. Q is equal to QP. It doesn't matter here in this case. Because the work is 0. If the work is 0, here, under constant pressure conditions, then delta U is equal to QP. But we already know that QP is equal to
Delta H.
delta H. And so delta U and delta H are the same thing. But we know that if we stuck this in a bomb, if I did this inside a bomb, would it make any difference?
No.
If I did the same, pour 40 milliliters into 40 milliliters, get 80 milliliters, it wouldn't make any difference outside or inside. And so this is the same thing as QV. So Q is equal to QP, which is equal to QV, which is equal to delta H, which is equal to delta U. This is how you want to go through, because you want to be able to make all the connections, you know, not just the ones I have here. So you should take this a step beyond and think of how are they all interconnected, you know. And so the correct answer would be how much heat is involved? Well, A, B, and C. But you know, that's the trick about thermodynamics. Thermodynamics is tough because, I mean, everybody had like, if you could learn thermodynamics like you learned words in elementary school, you know, like I remember when I was learning something like bear, you know, B-E-A-R, you know, some animal, right? And then there's other bears, right? B-A-R-E, whatever else, right? And you have all this time to learn all the definitions and, you know, and the context, like you'd use this bear for this and that bear for that, right? Those kind of things. In thermodynamics, people think, oh, I've already done that. You know, I don't want to do that again, you know? I had to go through all that vocabulary. And you did it at a very slow pace, right? So you learn it over a long period of time. But here, you have to learn all these little definitions, you know, in a short period of time. And they're all, like, complicated because the definition or changes, or the meaning changes depending on what the context is. And so that's what makes thermodynamics tough, because you got to learn all the contexts, you know, like Q, and put it in. The Q's like bear, you know, which bear are you talking about? It's the same thing. And but when you get to college, you don't want to do that anymore. You know, you just want some simple definition. Tell me the definition, one definition. You know, I don't want to learn multiple definitions for the same word. because you know, you say, I already paid my dues for that, but it's not, unfortunately, not the case anymore. You gotta still do it. And so the Q is the same thing, depends on what context you throw it in. And so this one, they're all the same, but they aren't always the same, you know? It's even more complicated. Does that make sense, though? That's for exothermic. For endothermic, it looks exactly the same. You know, if you go back and look at your notes, it should be there, I think.
It is.
Other questions on this? We can spend time reviewing.
I'll
do it.
Number 17.
17. Okay. Tell me, before we do number 17, tell me what is the definition of a formation reaction? It's the formation of
Gases in their natural state.
gases in their natural state. Not
Not
quite. Actually, this is not working for me. I'm go here. Let's see. The problem with thermodynamics is there's precise definitions, you know, and very precise definitions, like heat, you know. Oh my God, so many heats. But each one is precisely defined. And so let's see, enthalpy formation. No, it's not even, it doesn't come up there. Let's see, delta H. Is there a glossary?
So maybe it's
Right.
so elements in their standard state
Yeah.
react to form 1 mole of a product.
Yeah, that's it. All right, so that's it. It's the it's the formation of 1 mole of substance from their elements in their standard
Standard
states. So let's go back to this one and take a look. So automatically I can eliminate one of these. Which one can I eliminate? C. I can eliminate C. Why?
Plus 2 moles of
It's
H2O.
forming 2 moles, and the definition's for 1 mole. The amount of energy for 2 moles. And so it's got to be A, B, D, or E. So which one is it? B? Yeah, I'm forming 1 mole of NO2 from the elements in their standard state. So element O2, but NO is not an element. NO is a compound. And so it cannot be B because that's a compound. Maybe it's A. It's a formation of 1 mole, so we got 1 mole of HCl from the elements. Well, H is the element for hydrogen, but is that the standard state of hydrogen? No.
No.
The standard state of hydrogen is H2, the chlorine. So it can't be A. So it's got to be which one? D? It's got to be D then. And so it's formation of 1 mole of calcium carbonate from the elements, but this is forming from the compound, so it's none of these. It's got to be E, none of these. Uh-huh.
For formation reaction, does it have to produce a gas?
No. It doesn't have to produce a gas at all.
Oh, okay.
You produce anything you want here. So if we look at let's take a quick look at this. If we look at Appendix D, the reason why you have to have that definition memorized is because they don't show you the reaction here. They only give you the delta H for the reaction. And since it's only one type of reaction, it's always formation of 1 mole of substance. These are the substances from the elements in their standard state, and these are the energies, delta H is involved. And so here we form in solid, aqueous, gas, all the way to liquids. And so we can form any state. In fact, let's take a look at one of these here. We can see here there's a difference in forming gas versus liquid. If you form carbon tetrachloride gas, it's minus 102.9 versus carbon tetrachloride liquid, which is minus 135.4. It doesn't matter. But what does matter is the original state. You know, this is going to be formed from carbon. Does it matter? Carbon must be a gas. Is that right? Carbon gas plus chlorine gas yields carbon tetrachloride gas. No, the carbon has to be solid because that's the natural state of carbon. But not only does the carbon have to be solid, it has to be solid graphite or solid diamond.
Graphite.
It has to be solid graphite, which turns out to be more stable. And so graphite's thermodynamically stable of the standard state of carbon. And so this is the formation of CCl4 from carbon graphite plus 2 Cl2 gases. That gives it to us. Okay, other questions? Uh-huh.
Can we talk about 19?
19? As a delta H of formation, that is a standard enthalpy of formation of H plus equals 0 kilojoules per mole, and the standard enthalpy of formation of H2 gas equals 0 kilojoules per mole. That you've probably seen in the table here. If we go to the table here and just go to H, we'll see it here. The standard enthalpy of formation of H plus AQ is 0. The standard formation of H2 gas is 0. Both of those are 0 kilojoules per mole. That's true. That's true. Therefore, the standard enthalpy of formation of H plus AQ equals the standard enthalpy of formation of H2 gas. Is that true? A lot of people will say, hey, it's 0, so it should be, both are 0. So 0 equals 0, right? So what did you put down, true or false? True? This one, you know, some of these questions I might accept both answers, but this one I wouldn't. This one there's only one correct answer, I think.
Should be false.
It's got to be false. It's got to be false because why? One's aqueous and one's a gas? That's not the reason why.
Because in a standard enthalpy of formation, you want the standard state of the element, and if it's an ion, it's not the standard state.
No, it doesn't matter what we're forming. The standard state has to be the reactants.
Yeah.
The product need not be under standard state.
Oh, this is no product.
Like the standard state of carbon tetrachloride is liquid, but we can form carbon tetrachloride gas, no problem. It's not because it's an aqueous or gas or whatever.
I remember you said something about like the zeros are just arbitrary, right? Arbitrary points that we set by
Not
definition.
both the zeros.
Or,
1 0 is.
is it the H plus?
Yeah. The other 0 is absolute. So maybe an easier way is absolute might be tricky because you would think you wouldn't go negative. You can go negative here. So the easiest way to think about this is this. Is 0, hey, if I look at my thermometer, I see, there's a 0 degrees C. And then I have another thermometer and I see, there's a 0 degrees Fahrenheit. And so I see, both of those are 0. So that means 0 degrees C is equal to 0 degrees Fahrenheit. Is that true?
No.
Why not? They're both 0, so they both should be equal to one another.
No, different scale.
You would say false because they're both referenced to different 0 points. Celsius is referenced to 0 being the freezing point of water or the melting point of ice. Fahrenheit, what does 0 degrees Fahrenheit? What was that reference to?
Isn't it the freezing point of ocean water?
Was it the freezing point of ocean water? It's too cold. Ocean water doesn't freeze that low. Or does it?
Right along.
Is it? Is it the freezing point of ocean water?
It's dirty water, not like
Is it the salt?
Well, normal.
Right.
Yeah, salt ticks.
That's what they do for salt and ice.
.4 degrees Fahrenheit.
28.4 degrees Fahrenheit. Not 0. My understanding was this, that Lord Fahrenheit just predicted that 0 would be the coldest of winter days. It would be very cold. That's what I thought. So that was a scale, but there's got to be a better.
Oh, I know. Is the coldest point the repeatedly cool solution of water, ice, and ammonium chloride?
And ammonium chloride? Is that the actual way it was done?
Yeah, that's what it says. It says he did 3 temperature points that are freezing water, human body temperature, and the coldest point that he could repeatedly cool a solution.
Okay, so he had something consistent that he could repeat and then called that 0. Okay, that's fine. That's good. Thank you. I never. So that was close. Water. Just you put ammonium chloride in there instead. Ammonium chloride is pretty interesting. I don't know if you caught this, but I said Appendix D is very tricky. Is Appendix D, you have 3 scales in there. You have Fahrenheit, you have the Celsius, and you have the Kelvin. What was I talking about at that time? Fahrenheit, Celsius, and Kelvin. Appendix D. The problem is they don't have different units. They all have the same units, kilojoules per mole. And you might go, well, why didn't they write 3 separate tables to keep them separate? So you don't compare apples with apples. So you can compare apples with apples and oranges with oranges. It's because of the way the systematic error works. Remember I talked about, do you remember when I talked about systematic error in Appendix D? Anybody remember that? I know it was a long time ago. A lot of stuff has happened between then and now. But had to do with HCl. You remember that talk about HCl? HCl has a delta H of minus 167 kilojoules per mole. Delta H of formation of minus 167 kilojoules per mole. Does that ring a bell? Not at all. One thing that, it's like all this thermodynamic stuff is hard. And so what you do is, initially it seems like just like a random chaos and confusion and all that stuff. And so everything's totally disorganized in your mind. But the thing is, it takes time for your brain cells to organize the information, and then all of a sudden it clicks, Like all of a sudden your brain can make these connections between different things. But in order to make those connections, you have to go over repeatedly, in your brain. So you're thinking about these things. And even though it seems repetitious and it seems like you're not really learning anything new, but by going it over and over again, eventually things will connect. And so the whole talk was that there are 3 scales in Appendix D. One for the cations, so you can compare cations to cations. One for the anions, which is different. The 0 points are totally different for cations and anions. And one for the neutrals, compounds and elements. And so if I ask you this, this is where you take it to the next level. But the first thing is the repetition. You got to drill it. How do you drill it? Well, you just go over it over and over again. By going over and over again, your mind is thinking about these, and your mind, your subconscious, is trying to make the connections, for you. Your subconscious. And so if I asked you this, delta H of formation of H2 gas is equal to 0 kilojoules per mole, which is equal to delta H of formation of I2 solid, which is equal to 0 kilojoules per mole. Are those two zeros the same? Yes. Then it would be true. If I had framed it like that, that would be true. That would be true because those 2 zeros mean the same thing, because those 2 zeros are reference to the elements in their standard state. But for cations, we had a problem. The problem came up with HCl. Does anybody remember that? The HCl. What was the problem with HCl?
We were getting an error.
There's a systematic error for sure, but what was the problem? Before we got the error came from how we solved it. I said, at the time I said, maybe this might ring a bell, I said we have 2 unknowns, 1 equation. If we have 2 unknowns, 1 equation, then what we can do is we have 2 choices. 1, it's impossible to solve, or 2, we do what?
Assume 100%. No.
Not assume 100%. It turned out it was a 2 equation, 2 unknown, and well, I don't want to review the whole thing.
I have it written down
because,
that H plus can't exist on its own.
Does anybody have this in their notes?
Yeah.
Yeah? All right. So the problem was this. We're forming 2 things. We're forming H plus A cubed, this is a strong electrolyte, plus Cl minus A cubed. And so the question I asked is, what of this 167 is attributed to H plus,
And which ones to see?
and what to chloride? And so this is X out of the 167 will be H plus, Y out of the 167 will be chloride. So we have 2 unknowns. The 2 unknowns is how much heat was involved in the formation of H plus and how much heat was involved in the formation of Cl minus. We have the total amount of heat. The total amount of heat is the amount of heat required for both H plus and Cl minus. But what we need to do is we need to separate into individual. Does this now start to bring back some memory? You know?
So then I have under the two arrows, we assume 0% for X and 100 for Y.
Yeah, I mean, we could come up with 50-50, 25-75, but those are just guesses. So
Yeah,
we're going to
so
do
then
guesses like that.
You'd add the errors up to get the answer.
Right. Either way, we're going to need an error. It's going to be a systematic error. And so the systematic error cancels because you cannot form a cation without an anion. So we talked about this. This is very critical for Appendix D. If you don't know Appendix D, then you might compare numbers like this. You might compare a number. Like you might go, hey, if I look at iron's 0, but iron 2 plus is minus 89.1. That means iron 2 plus is much more stable than iron. Is that correct? It's wrong. It's wrong because we cannot compare these two numbers. I could compare iron solid with FeO. That's no problem. When I look at FeO, it's more stable. And so I'd take iron solid plus O2, and FeO would be more stable. Whereas, what would be less stable? Or I could take, iodine solid and go to ICl liquid. That's more stable. But if I go from iodine solid to ICl gas, that's less stable. And so we could use the numbers there to make some simple comparisons, as long as we're comparing apples with apples. But this table consists of apples, oranges, and grapes, yeah, whatever, peaches, And so you can't compare a peach to an apple, And so that was the point of that question.
So it should be false.
Yeah, that's false because that's comparing. That's like saying this. What would this be like saying? To me, this would be like saying, 0 degrees C is the same thing as 0 degrees Fahrenheit. That's what it would be. Okay, so the answer is false. Okay, other questions from the practice test? Number 7? Let me just check one thing here. Solid ammonium nitrate is decomposed in a constant pressure reactor. Is any work done? So ammonium nitrate is decomposed at constant pressure. Is any work done? And so what you have to do is you look at delta V. Was there any change in volume?
Yes. You went from less volume to greater volume.
It goes from less volume to greater volume? How can you tell?
Gas formation and liquid formation.
Yeah. So the solid, 1 mole of ammonium nitrate doesn't take up much space. It'd be like this much, 2 moles of liquid water doesn't take up much space. 2 moles of liquid water is 36 milliliters. Doesn't take up much space. Ammonium nitrate's about the same density, so it doesn't take up much space. But N2O takes up space. N2O, that's going to take up how much space roughly? 25 liters. So the volume is going to expand by about 25 liters. If the volume expands by 25 liters, was work done? Yes. Yeah, work's got to be done. Now, you know, if you have the luxury of time, you would go, okay, let's try to understand this deeper. Was work done by the system or was work done by the surroundings? Who did the work? The system or the surroundings?
The system did the work.
The system did the work. If the system did the work, would that be negative or would that be positive?
Negative.
That would be negative. Could you calculate how much work was done? Yeah. And so these are things you do as a follow-up. What would what could I do to make this no work done? What could I do to make B the correct answer? If I did this under constant volume, if I did a constant volume reactor, then would any work have been done? No. The volume can't change, so no work could be done. And so you start thinking about that to get some variation, you know, to make it a little bit more challenging, or to try to understand it a little bit deeper. The same thing I do, like with the notes. You know, when I go through my notes, I would try to summarize everything in my own words, not, you know, what I was told, but to think. And then I try to think of it from different perspectives, or ask, you know, different variations of the same question. All right, other questions? Uh-huh. Number 33.
The 4.
The 4s orbital is more penetrating than the 3d orbital. That's tricky because the 3d orbital is much closer, and the 4s orbital is much farther away. You know,
But
as
in
far as
terms of
effective
energy-
distance goes. Hmm?
But in terms of energy, they're different.
Yeah. So it's on the one hand, I would say 3D is more penetrating because an n equals 3 in general is a lot closer to the nucleus than an n equals 4, right? But on the other hand, I would say 4s is more penetrating than a 3D. Why? Because I've memorized something. And this is something everybody has to have memorized, is the orbital energy level diagram. The orbital energy level diagram shows something funny when we get to the 4s. You know, if I have a 3s, 3p, the next orbital we expect is a 3d. But instead we get a 4s. And so the way it goes is this. The way it goes is 3s to 3p. And then we expect to go 3p to 3d, but it doesn't. It goes 3p to 4s, and then 4s to 3d. So why did the 4s sneak in front of the 3d? The 4s snuck in front of the 3d because it is more. In general, you would expect it to be higher in energy because it's further from the nucleus. But
It's also the RDF graph.
yeah, basically you would see it in the RDF. And we could see it in the RDF here. So which chapter do we want to use for the RDF? Chapter 9 or chapter 8?
I think we discussed it in 9. No, in 8.
And we discussed it in 8, but there's another RDF in 9. With the size. With the size. Ah, shit. All right, this doesn't show it, unfortunately. And so 8 would probably be better. Let me just go to PowerPoint. I don't know if 8 shows the 4S.
Yeah, it's okay.
It shows a 3S, 3P, and 3D,
No, 4S.
but not the 4S. Well, here you can kind of get an idea of what the 4S would look like. When you see orbitals that look like that, we can imagine the wave function. When we imagine the wave function, look at that 3S. The 3S starts off like this. This side. It's a higher energy orbital is going to have a higher probability that the electron's further from the nucleus. That's what we see over here. So when we look at psi squared, this is just looking at one side of it. It's going to look like this. And we have two nodes. That's the 3S. So what does the 4S look like? Well, the 4S is going to be like this. And we look at the probabilities. We see that the 3S is going to be penetrating. Even though the bulk of it is out here, do you see some probability here?
Mm-hmm.
So the highest probability is going to be out here, though. It's going to be the highest probability. And so if we could shade this, you know, the outer shell right there, the blue would be darker. And the inner blue shell would be a lot lighter because it's lower probability. But still, there's probability there. And so what would the 4S look like? The 4S would look like, if you look at the psi, you could flip it the other way as well, but this one's going to end in a red. So this would be the 4S. And so comparing it here, we can look like this. And the 4S, you'd see it's further out, but still we got this blip here, which means it's fairly penetrating. Now let's compare that to the 3D. If you look at the 3D, this is the radial part of the wave function. We're going to skip this. We just want psi. This is half of, and this is much the probability. We look at the 3D. Does the 3D have any kind of blip near the nucleus here? 3D. So even though we don't, we have the 1S, we have the 2S, then we have the 3S. But if you look at the pattern, the 4S is going to look very similar. It's just going to have no more hump in there. But it's going to have this little blip in the nucleus. A little blip shrinks, but still it's more penetrating than the 3D. All right, so going back to the original question, let's see, what was the original question? The 4S orbital is more penetrating than 3D. The answer is true, and it's true based on our observation of this diagram, the orbital energy level diagram. Orbital energy level diagram, which will show here. This orbital energy level diagram is not enough. Does this orbital energy level diagram show it?
No.
No, this one's too weak.
We're missing 4S.
We're missing the 4S and we're missing the 4P. You know, I'd at least want to see the 4S and the 4P. So can you put that in here? Well, you could, actually, yeah, now I remember this energy level diagram. A lot of students go off the book. And so on the test, a lot of students were able to do this, but they weren't able to put the 4S and the 4P in here because they never studied beyond the book. Right?
4S would be below 3D and above 3D.
Yeah, 4S would be between these and 4P would be above the 3D. Let's get a decent orbital energy level diagram here. So here's one from dummies.com. This one is no good. Why is this one no good? Where's this one from? NPAP chemistry. No wonder. That diagram is no good. Unless oh, that's awful. Why is that awful? Now, I've seen this. Now I know why I've seen this, because maybe people were searching online. I've seen it where people, how many p orbitals, 3 p orbitals are there? 3. I only see one orbital there because I just see one line. So that's why I blew it up to see if there's a gap. But and how many d orbitals are there? 5. I guess they're trying to do it by the length of the line, but can you tell by the length of the line? Is there some kind of scale? No. So this is awful. It doesn't show me all the states that are available. So unfortunately, this is very bad. This is good. The one from Dummies is good. This is good. Somebody's hand-drawn one. This is acceptable. This is bad.
This is like half of the NLM notation.
Well, the 4P, the position of the 4P. Wow, this is UC Davis, but I don't know who made it though.
Alright. Don't trust
You know what? But I'm not telling you everything because it depends on the size of the atom. The 4S is above the 3D for certain size atoms, and it's below the 3D for other size atoms. So it depends on the size of the atom, the position. But for the most part, it's below. So you might as well just memorize one. I don't want to have you memorize a bunch of them. And so the ordering here, this could be the correct ordering. This is from UC Davis. This is 4S to 4P. Oh no, 4S to, let's go a different one. It's helium. Let's go to some more. Oh, here. This is okay here. Let's see, is this okay? Is this one okay? This is the diagram for most elements. And so, like I said, there are some slight variations, but 4S to 3D to 4P. This is when we get all fancy with the orbitals. We're going to do a little bit more fancy stuff later. And so if you have a diagram like this memorized, then that's fine. What is that orbital? Can you tell me what orbital that is?
1, 2, 2 nodes, 3, the third
Yeah.
orbital.
This is a 3s orbital.
3s. So are nodes only when it's like it touches the x-axis and goes back up, or is it when it crosses?
It can touch and go back up, or it can cross.
Oh, it can cross, okay.
All right, this is the diagram. Actually, these two diagrams you need to know. Both of these.
One's for hydrogen and the other.
Yeah, one's for hydrogen or one electron, the other's for multi-electron. So. All right, were there other questions on the test? On the practice test? Yeah. 40?
41, you said pick 2 electrons to label with 4 quantum numbers. What do you mean by that?
What do I mean by that is, I'd have you take all the electrons and label them. But it'd get too messy. And so you could just pick any 2 electrons in an orbital energy level diagram and tell me the 4 quantum numbers. The first 3 quantum numbers identify the orbital. The 4th one just tells me if spin is up or spin is down. And so let me go to the 99D orbital. Do 99D orbitals exist?
Mhm.
Yeah. Okay, let's say I want to do this electron in the 99D orbital. What are the quantum numbers for that electron?
So D is 3, so L is going to be 2. So L is 2.
Is D 3?
0 is SP. Oh, 2. So it
2.
should be 1. L
Yeah.
is 2.
Yeah, so this is going to be 99, 1.
1, 2, 3, 4.
Is that right? 99, 1 or wrong? No, this is 99,
2.
2,
4.
4.
Wait, no, I got that wrong again. 1.
No, this is going to be 99, 2, 1, negative 1/2. That's right. So that would be an N, L, M, and S. And so you should be able to pick any electron. You just pick that. That would be that one. You should be able to pick any electron in any orbital and tell me the 4 quantum numbers for that. This is not arsenic. For arsenic, we wouldn't have this. For arsenic, we'd have 4p. You should be able to tell me the quantum numbers for each of those. Oh, I got it. Next class is coming in. Sorry. If you have more questions, you can. Yeah.
Do you know the constant for like memorizing C or?
What's that?
Do you know the constant?
No, you don't have to memorize the constants. I'll tell you the constants. If you guys have more questions, you can ask me. Let's step outside here because. Oh, okay. Okay, that's fine. I forgot to give you a little preview.